Okay, 6-2A.
At least hyper children today, goodness.
I know, right? All right, we're going to learn all about the second branch of, we started it, the second branch of calculus. We're going to do definite integrals. There's going to be infinite integrals, but today we're going to do definite integrals. Okay. So integrals, this comes from the 1800s, actually, when they discovered calculus. That would be a pretty cool time to live. I've taken 2 courses on the history of math.
For fun?
No, they were requirements. Yeah, the first one was a requirement for my undergrad, and then the second one was a requirement for my master's. All right, so first thing we're going to talk about is something called Riemann sums. Riemann. That's how you pronounce it, Riemann. No, Riemann sums, they come from a man named George Riemann. He lived in the 1800s. He actually died at the age of 40. I know, really sad. Yeah. The mathematicians of the 17th, 18th century, they assumed the existence of limits and Riemann sums. And then George, this guy, he came along and proved what they were all doing. So he was pretty much a genius. So here we go. Now this is what a Riemann sum is. Suppose that you have a function, and yesterday we did, all the functions were positive functions, but functions can dip below the x-axis. They can be negative. And so if you had something like this, for example, okay? And if you were going to find the rectangles that go with this one, you know, all these rectangles here, what happens is this ends up being a negative area. Negative area. And the ones above the x-axis, these ones up here, all of these, those are all positive. Positive area. Right here in blue. Okay? Now, what you are essentially doing, and I'm going to teach my Algebra 2 kids this symbol in a minute, not a minute, in a day actually. You're taking all of these rectangles and you're adding them up, right? You're taking A1 plus A2 plus A3 plus all the way, and there is, say, n of them. Yeah, remember this guy?
Yeah,
Sigma, summation, Sigma notation tells you for this, you start at k equals 1, and you go to n for a sub k. And that sigma notation means to just add them up. Do you remember this? You plug in 1, and you get a sub 1. You plug in 2, and you get a sub 2. And you do that all the way until the last number, which is a sub n. So it's just another way to write that. It's nice and clean in sigma notation. You did stuff like this in Ham. I think Ram did this too. N equals 1 to infinity. Remember, infinite ones? Of, say, 1/2 to the n. And that's really fun to do. This is the one that freaks people out because they're like, what? That can't be. But this is to go ahead and take 1. So you're taking a half. And then you're adding it to what? A fourth. And then you're adding it to an eighth and a 16th. And you do that all the way out to infinity. It's not negative 12.
What's the one that's equals negative?
I don't know.
Mr.
This
Beck
one
told us.
looks like this. You're going to take a half.
I swear.
Here's 1/2. Then you're going to add a fourth to it.
Does it equal 1?
And then you add an eighth and a 16th. And if you do it an infinite amount of times, it actually covers the entire circle, and it equals 1.
Which is the one that equals a negative number? There's one that equals,
Yeah, there's a bunch of equal negatives.
but like a weird one that you
Oh, I don't know that one. Now, for the Riemann sum, what it does is it's going to take all of your rectangles here that you did yesterday. So this is what it does. It takes the sum of the length times the width, right? You guys did that yesterday. It was the length, the bottom part, times, or the top, the height times the width, whatever you want to call it. And if you did this over an interval, you did it from A to B. okay? Now, what we're going to do is we're going to kind of change that, because when you did this yesterday, how did you find, bless you, Jack, how did you find that height? What did you do? F of, yes, F of whatever, F of 0, F of 1, F of whatever. And then each of those widths on the bottom was just an increment of x. So this is what we're going to write instead. We're going to go like this. Here's our sum from n equals 1 to f of x sub n, whichever f of x we're doing, times the width, which they call delta x, because it's the change in the x each time. Okay? We're going to do this on an interval from a to b, and we're going to go ahead and go all the way to k, and we're going to take the limit of this whole thing as k goes to infinity. Yes. Yeah. No.
I said yeah.
Okay? What this means, I'll tell you what this means. This means to take each rectangle and add it up until you do it an infinite amount of times.
So you have to add them all up?
Yes. So let's say that we have some curve, okay? I'll do it in a picture form. And let's say we have this curve and we're trying to find the Riemann sum, or the sum of all the rectangles in here. But when you do this an infinite amount of intervals, then you get the teeniest tiny little rectangles, and what happens is this. It actually gives you the exact area you're looking for, because you have an infinite amount of them. It's like going to infinity is the key to all of this. And it fills them all in and you get the right thing. Well, guess what? They don't write it like this. They're going to write it like this. This is what this is equal to. Here we go. Now, if you're in physics, you might have seen this symbol, but it's called the integral. That's what this is. Yeah. See that S? You know what S stands for? Sum, sigma. It's a sum. That's what an integral is. It's a sum from A to B for f of x dx. Now, where did this f of x and dx come from? Well, guess what? See, this is f of x. Dx is the differential of x, and that's going to be the integral. Some people say it's the integral from a point A to a point B for f of x with respect to x. It's always with respect to x. So like if you were going to take the integral from A to B of f of u, but you would have then du, okay? No, that's actually in the book. They actually use that as one of them. Or if you were going to take the integral from A to B of f of t, it would be dt on the end, okay? What's so funny? No, nothing? The f of u? No, you shouldn't have. You say that every time and then you get it.
No, I don't.
Yes, you do.
The only reason why I understand is physics.
My favorite is,
What we're doing right now.
I still understand.
all we did was I showed you that.
Why are we doing that?
Well, because I don't want to just give it to you. We're deriving it.
I know, but like, what are we putting in those?
So we just learned that this is written as this now.
So we just need the bottom one.
Yes. Yeah. We derived this. Like, what is an integral? Well, that's what it is. To take the summation of all of your rectangles, and this is just a nice way to write it. So here, I'll give you an example of what you'll do. Number 1. All right, let's go ahead. Let's say we have this sigma. We're going to take the limit as n goes to infinity.
Wait, why'd you write it like that?
For k equals 1, they write it, however, like variables, to n of 3 m sub k squared minus 2 m sub k plus 5 delta x on the interval from -1 to 3.
So ugly.
It is ugly. And you know what? We're going to make it nice. That's what we're doing
What are they
here.
asking us to do?
We're going to express the limit as an integral.
Why'd you use K?
They don't have to use n or yx because it's going to be an integral of x.
So why is there not X anywhere else in the book?
We're going to make it that way. Express the limit as an integral. All right, this looks super gross. Everyone's all complaining about it because you should. It's gross. We don't like it. And so what we're going to do is we're going to change this into its integral form. Okay? So this is what it's equal to. It's equal to the integral, so you're going to use that symbol. And then from a to b, so the integral from -1 to 3. And what we're going to do is we're going to change all of these in here. And this is going to be our function of x now. It's f of x. That's what the integral does. See? It takes this f of x sub n or whatever that is, and it makes it f of x dx. So let's go ahead and write this as a function of x. So that would be 3x squared minus 2x plus 5. And usually they'll put parentheses around it. And then you want to change delta x to what? Dx. And that's it. You don't have to solve it. All we're doing is expressing this limit as an integral. Yes? This? Right here. So, yeah, so our interval was from a to b. So on the integral, it's from a to b. And that's all they're asking you to do. Make this ugly thing that's really gross and bad looking and rewrite it in its integral notation so that you know where it's coming from. You're not solving it yet. We're going to. You could solve it using that. I'm going to show you that tomorrow, but spoiler alert. What's that?
MK is just X.
Yes. Yep. Exactly.
What is the K equals 1?
Yeah, so k is going to 1, and then it's 2, and then it's 3, and then it's 4, and it's going all the way until infinity. So basically what this means is you're taking all of, see this is a parabola? You're taking all of the y values times the little, you're making all these rectangles in there, but it's going to be a limit as it goes to infinity. All the rectangles are getting filled in. Okay, so that was A. Now we're going to do letter B.
Are we solving now?
Yeah, we're going to solve some. Okay, we're going to talk about theorem number 2, and you're probably wondering, where did theorem number 1 go?
We're done solving 7, 2.
Theorem 1 is just that integrals exist. That's actually a theorem.
How can you prove that?
You actually do in advanced calculus, and that's when that was a really hard class. You had to prove all the theorems from calculus. So, okay, theorem 2 is called the constant theorem. This is what the constant theorem says. Shh. It says this. If you have an integral from a to b of c dx, okay? If you have an integral of a constant, okay, not a function of x, okay, just a constant. A constant would be a line, just going straight across. This is going to equal c times b minus a. That's what theorem 2 says. Okay, that's how you evaluate this integral. We're going to evaluate the integral. Now, do you remember when we evaluated derivatives? It was always the slope of the tangent. Integrals are the area under the curve. Okay, so we're finding the area under the curve. Sometimes it's not curvy, they just call it a curve. This case it's a straight line. So let's draw this real quick.
But can't you just like do a...
Yeah, I'll show you. So this theorem makes sense. I'll tell you why. If we have a constant, y equals c is a constant. That would be a horizontal line. Let's say that this is our y equals c. Okay? So this goes to c. And if we're trying to find the area on an interval from a to b, what are we finding the area of? A rectangle. Okay? And what's the height of this rectangle? C. And what's the length of this rectangle? B minus A. And so it's C times B minus A. It's almost like a proof almost.
Why can't we just do C times B minus A?
You can. I wrote it right here.
You took notes, you realized to write it down.
You can, but I want to show you that if you forget that, let's say you forget it, it's a theorem, you might not remember it, then you can draw a picture and you can always get your answer. So let's do some. Here we go. What are we on, number 2? 3, 2. Okay, let's go ahead and find the integral from -1 to 4 of 6 dx. Integral of -1 to 4 of 6 dx. Some of you can do this in your head. Okay, some of you can't, that's okay. So if you memorize the formula and you know it, it's just 6 times 4 minus -1.
I'm just waiting until we get to the stuff we did.
Oh, that's not going to be for a while. 30.
That stuff was
Nice, right?
hard.
That should make sense because if you have y equals 6, you have -1 to 4, then you're finding the area. It's always the area under the curve bound by the x-axis, okay? That's the integral right there. How are these related to derivatives? Well, we're not there yet, but it's very powerful. Okay, part C, last part.
So we did part B literally like.
Oh yeah, that was part B, theorem 2.
So I have theorem 3.
Do you need more than that? You got it.
Now it's left.
Yeah?
Just the,
Do they always give you a positive number? I think. Oh, if it's underneath, then the area would be the opposite because it's going to be negative. You know what I mean? Yeah. Here's the thing. If they ask you for the integral from say 0 to 4 of -3 dx, the integral is equal to -12 because it's -3 times 4 minus 0. The area of it is 12. Okay? So that's a little tricky. The area is negative when it's underneath, yeah. But if they ask you for like the area of the region, then they want the positive answer. I'll be very clear on whether you're going to have a positive or negative. If you're just evaluating an integral, then it's -12. Yeah.
So area is just like the absolute value of the integral.
Yes. Yeah. Yes, we're going to talk about that on a different day because you have to, like, if you find the integral, you'd have to subtract the area and add the area and then yeah.
So just for now, the area is
Just for now. Okay, last part, part C. Now we're going to do exploration number 1 in your book, but I'll go ahead and write it out. You don't have to get your book out or anything. Exploration number 1. All right, now they're going to tell us this. We're going to have the good old sine wave, which you all know and love. 1, 2, 3, 4. There's 2 pi. Here's pi. Do you remember this sine wave?
Yeah.
1, -1. It goes through 0, 0. At pi over 2, we're up here at 1. At pi, we're at 0. Down here, right there. All right, so here's the sine wave. Gorgeous. Don't you miss graphing these? I know, aren't they fun? All right. Now, so this is just f of x equals sine x. All right, I'm going to tell you something that you probably don't know yet. It's very exciting. See this in here? It's 2. Exactly. Bless you. Oh, is that funny, Jack? What's so funny about that? Nothing. Oh, he did? Yeah, that's normal. Okay. The area in here is equal to exactly 2. It's not 2 point something. It's not pi. It's 2. And it's not a semicircle.
So I went -2?
Yes. The integral of sine x from 0 to 2 pi is 0. Dang. Okay. So cosine. Yeah. Same thing. It's also 2 in its little curve. All right. So this is what we're going to be given. We're going to be given that the integral from 0 to pi of sine x dx is exactly 2. We're given that. I'm going to show you how you get that later on, but right now that's just a given. So what we're going to do is we're going to do some problems here. So number 3, we're going to find each value. We're going to evaluate. So we're going to get a number value for each of these. And I've got a bunch of them. So letter A, we're going to evaluate the integral from pi to 2 pi of sine x dx. Okay? Just given that the integral from 0 to pi is sine x dx is 2, then we're going to be able to find this. And what would the answer be? -2. Perfect. Okay? This right here is from 0 to 2 pi. It's exactly the same shape. Okay? It has an area of 2. The integral, though, is below the x-axis. So it's a negative area. So it's going to be -2. Okay? All right, let's do some more. These are so much fun. Letter B. How about the integral, oh, we just said this one, 0 to 2 pi sine x dx? 0.
So there's no
No?
math we're really doing. It's just
Yeah.
knowledge of what you're doing.
Oh, yeah, you're doing positive 2 plus negative 2. There's math. All right, we'll go up here. Letter C. What do you think, use your most educated guess, of the integral from 0 to pi over 2 of sine x dx is? 1. Why am I here? 1, yes.
Who said that?
Trevor said that.
That's not hard. That's 2 divided by.
That's what I'm saying.
Yeah, he's saying it's too easy for him.
Oh, I thought it was
He
too
should
hard.
be an AP Calc is what he's saying.
How do you say 1 million comes?
No. This is from, we're given this piece of information, so from that we're learning all of these, because that's not a constant. Theorem 2 was the constant graph. This is sine x. Okay, guess what?
We're done.
I'm going to give you a harder one.
Thank you.
About 0 to pi of 3 sine x dx. Yeah.
That's not hard.
Okay, what you can do here
1.2 by 3.
is you can take any constant out like this.
We learned that.
You did in physics.
Yeah, I took that class.
Shredlin, he's so good. And you get 6. Good. Okay. All right, you want a hard one? Here we go then.
You said that about this one.
No, here's really a hard one. And a lot of people get this
I'd
one
like
wrong.
to get to my impending fate like fast. Like I don't need it to be like.
What's that? Here we go. Integral from 0 to pi of 2 plus sine x dx. And the answer is not 4. All right.
Okay, let me figure it out.
Yeah? You feel like it's going to be 4 because the last one was just 3 times 2. And this would be 2 plus 2, but that's not right. Nope.
Because when you distribute the dx, it's 2 dx now, it's not just dx. So you
Right.
just bring the 2 to the front and multiply.
Yeah, you can't do that. Now, if you were going to split this up into 2 integrals, you can, because this is 2 different functions and you can split up integrals. This is the integral from 0 to pi of 2 dx plus the integral of 0 to pi of sine x dx. Okay, one of them I know for sure, and that's this one right here, this one. They told me what that was. What is it? 2. Okay, this one comes from the constant theorem that I just told you. Isn't this the integral of a constant?
Oh, yeah.
And how do you find the integral of a constant? 2 times pi minus 0. Yes. So your answer is 2 pi plus 2.
It's not 4 pi.
It's not 4 pi. It's not 4. Let me show you why in a picture form, okay? Do you know what 2 plus the sine x is?
Yeah.
It's just the graph has been shifted up 2, right? And so here's your graph. It looks like that. And so what I'm trying to do is I'm trying to find this area, the integral from 0 to here. Look what it makes. It makes this thing up top, which I know is the area is 2, and then it makes this rectangle. See that? So that's why I got 2 for that, and this was from 0 to pi with a height of 2, and that's the rectangle. Pretty good.